Hello, I am trying to start this presentation. Hello to the audience at the 7th Brazilian Congress on Neurovision. My name is Stephen Loew. I've been invited to send a presentation via video from Australia, and I wish to thank the organisers of the Congress at UFMG and LAPAN for being kind enough to invite me to send a talk. So, as you can see, my topic is visual stress, which is the condition that affects reading, and it is also a condition that I have. I was diagnosed 25 years ago, so I have a vested interest in this subject. Now, I better begin with the presentation. Time is short. First of all, what is the condition visual stress? The words describe visual discomfort, but the condition describes unusual levels of visual discomfort, especially when reading. And it is also known as Mears-Irvine syndrome or pattern-related visual stress. It is a very common visual processing deficit. It causes this visual discomfort to the extent that reading is affected, and at least 12 to 14% of the population experience these symptoms. 5% experience severe symptoms that can actually cause a reading disability, while the rest experience moderate symptoms depending on the lighting and brightness and so forth. And most people are not aware that they have the condition, as this processing deficit is there from birth. So, sorry, sip of water. A little nervous, I guess, camera. So the key symptoms are sensitivity to light, particularly fluorescent lighting, and also heightened sensitivity to high contrast repetitive patterns, such as black stripes or lines on a white background. Unfortunately for people with visual stress, the spacing between the strokes of letters and words and the spacing between lines of text is close enough to evoke these symptoms, visual discomfort, and in their case, and in my case, they experience visual distortions of the text they are reading, such as words moving or vibrating, which of course leads many people to have headaches or migraine problems. And generally, people with visual stress are slow readers. A key characteristic is that if they're reading orally, as I am now, after a short period of time, their reading deteriorates. Now, as I said, these symptoms are known to be exacerbated by fluorescent lighting. However, numerous studies have reported that the symptoms are significantly alleviated by the use of spectral filters. In other words, coloured lenses, such as what I wear, or coloured plastic sheets that are placed over a page of text. Removing the white background is a great help for a start. Now, it's important to know that although visual stress affects reading, it generally does not prohibit reading. And in fact, many people with visual stress are quite proficient readers and such as PhD students and academics. But it is not the same condition as phonological dyslexia. The two conditions are distinct. However, the prevalence of visual stress in the dyslexic community is far higher than in the general population. At least 20%. Many researchers say that we can assume 1 in 4 people with dyslexia also have symptoms of visual stress, which compounds their reading problems. As for underlying causes, there's been much research pointing towards slight delays in the signals being transmitted from the retina to the visual cortex along the magnocellular visual pathway. And these slight delays could in fact cause most of the symptoms I've described. However, more recent studies using fMRI technology have shown hyperexcitability of the visual cortex in people with visual stress when they're reading. The area of brain activation that lights up in these scans is many times greater than in normal readers. And importantly, these studies have also shown, or some of these studies have shown, that when the same people read through spectral filters of a color that they prefer, this enormous brain activity in the visual cortex reduces to almost normal. This is important because these fMRI studies were also the first highly objective hard evidence that the condition visual stress exists. Although in the last few years, researchers at La Palme, using eye tracking technology, are adding to this hard evidence. Now, the reason for this talk is the same reason that I undertook a PhD a few years ago, because I hypothesized, I always have trouble with that word, that declining rates of literacy and numeracy in Australia, which is a huge issue, it's in the news and discussed by politicians almost every day for the last 15 years or 20 years. My hypothesis is that perhaps these declines in literacy, reading and numeracy, may correlate with changes to the lighting in schools, particularly primary schools. So I investigated how lighting has changed in primary schools since 1970 as part of my PhD. I focus on primary schools because you do not learn to read in high school. In my case, I learned to read in primary school under this form of lighting, incandescent lighting. But by the end of the 1970s, the lighting that was in high schools was installed in primary schools. And when I entered high school, before that happened, I'm showing my age, I became a slow reader and a daydreamer. But I had learnt to read under a more natural spectrum. As incandescent lighting, the spectral curve here is smooth, continuous, and very similar to sunlight, kerosene lamps, all forms of light except for fluorescent lighting and now LEDs. I also found that by the year 2000, lighting engineers and manufacturers had evolved fluorescent lighting to include far more blue, far less red, and also far more violet. It does not look much. I hope you can see my cursor, but if you compare the equivalent spot here, the ratio of violet and blue is very small compared to yellow, orange, and red. The reverse is the case in this form of lighting, which is now the standard lighting. So one might say, can people actually notice this difference? Well, if you look at the lighting, you will. This lighting is very similar to how lighting would have appeared in an office or school 20 to 30 years ago. And this is how modern day lighting appears. The only difference is both of these sets of lighting are in the same room, but for the purposes of an experiment I did at the University of Oviedo in Spain as a research attachment, I placed filters over the tubes of one set of lights, and these filters were designed to only filter blue and violet to some degree, and virtually not filter the rest of the spectrum. So this is approximately how lighting was 20 to 30 years ago. 20 years ago. If anyone is interested in that study, which showed that visual stress affects highly proficient readers, as all the subjects were PhD students or academics, professors, this is the reference for that paper, and if you have trouble obtaining it, you can, I'm sure the organisers can provide you with a reference or my contact details. Now, I better move on because the time limit is short, and as you can see, I've put far too much information into my slides. But it's a complex issue. So apart from the spectrum of lighting changing dramatically in the last 30 years, there's also an issue of how much lighting. The problem is that over-illumination has tended to increase in the same period. And not only that, but the type of illumination with the added blue and violet appears to the human brain to be brighter anyway. So there are more lights, and each light is brighter. A study in 2009 by Winterbottom and Wilkins. Arnold Wilkins is the leading researcher of visual stress in the world and has over 100 papers on the subject. They looked at 11 schools and 90 classrooms in Britain, and alarmingly, they found that 88% had significantly excessive illumination. And what's worse, 84% had highly excessive lighting, which was judged as being 1,000 lux, a measure of lighting, or greater. As there have been a number of papers published which indicate that interior illumination over 1,000 lux causes visual discomfort. Worse still, the mean illuminance of these 90 classrooms and hundreds of desks was well over 1,000 lux, and amazingly, the difference between each student's desk and between each classroom in illumination ranged from a mere 38 lux, which is enough for a hallway, but not quite enough to read, to 2,500 lux or more, because the lighting meter they used, a lux meter it's called, the maximum limit was 2,500, and it reached that. So it could have well been 3,000. Now, here's a reference for that paper, Lighting and Discomfort in the Classroom, if anyone is interested. And this raises the question for many people, why is over-illumination so common then? And this is interesting because government statutory authorities, which are bodies tasked with recommending various standards for buildings, including the amount of lighting. They recommend lighting level standards for schools, offices, universities, and in the UK and Europe, the guidelines that are used have this number, which can be Googled. And in Australia and New Zealand, we use AS is Australian standards, NZ, New Zealand standards. This set of guidelines, both of which are shown here, or an excerpt of both, relating to educational facilities. Now, the problem is that the lighting industry also recommends lighting levels, which I think is a conflict of interest. And as you'll see, this example of typical lighting industry recommendations for the same conditions, general classrooms, exams, is far higher. For example, laboratories and practical rooms in Australia is 320 lux, and here it says in certain conditions local lighting 800 lux maximum. However, the lighting industry says it should be between 500 lux and 1,500 lux. Now, if that is not enough, the paper manufacturing industry has changed the brightness and whiteness of the paper we read from under this excessive lighting. This is the reason that is nowadays marketed as ultra white paper, because the paper is far whiter and brighter than any prior examples in the history of mankind. To explain how much it's changed, I need to explain how it is measured. And in Paris, the International Lighting Commission, or Commission Internationale de Clairs, several decades ago formulated a whiteness index called the CIE whiteness index. Excuse me. It's cold here, it's winter, and I have a cold. Excuse my voice too. So I'm meant to be watching the time, but I didn't start it. So, prior to the 1990s, with the best bleaching technologies available, the most expensive papers could attain a CIE whiteness index of 75, perhaps 85, maximum. Today, if you walk into a supermarket, you can buy printing paper, and on the side of the packaging, it'll clearly say or boast CIE 170. You'll see 160, 165, 152. Below 150, it usually says nothing because the manufacturers are perhaps embarrassed that it's not ultra white. And this raises, I'm sure, a question with some of the people in the audience. If the maximum whiteness possible is CIE 100, and in fact, snow is less than CIE 100. Snow has a CIE of 99.8 or thereabouts. So how is it possible that paper can be whiter than the maximum whiteness possible? And the answer is simply that because of competition with the arrival of personal computers and a huge demand for printing paper, paper manufacturers decided to compete with each other on how white their paper is, and they turned to fluorescent chemicals, which they call optical brightening agents, or OBAs. These capture the invisible ultraviolet light emitted by fluorescent lights and sunlight, in fact, but not so much from incandescent lighting. They capture the significant amount of ultraviolet light from typical office and school lighting. They then re-emit it, which is fluorescence, at a lower wavelength, which is visible. So they add visible light. In other words, the paper reflects to the eyes of the reader more light than visible light than it obtained from the light source. And all of this light is deliberately designed to be in the blue band of the visual spectrum, because that is the area where the human visual system is most sensitive, and therefore the human brain perceives added blue as additional brightness and whiteness. Now, I'm not sure how we're going for time here. I forgot to start my clock, so I'll have to speed up. As you can see here, and just briefly, there are two types of photoreceptors in the retina that we actually see with. There's a third one concerning circadian rhythm, but we do not see with that. Now, the photoreceptors called the rod cells are responsible for or enable us to see in very low lighting conditions, such as twilight or nighttime, moonlight, and this is called the scotopic response. Now, here are the sensitivities. And the cone cells are responsible for giving us the ability to see in very bright conditions, such as broad daylight in summer. Now, it was long thought that the rod cells, or the scotopic response, was our night vision, and the cone cells photopic response is our day vision. But it's now well known since 1990 that both of these visual systems overlap with sensitivity, and both of them function in typical interior lighting, up to at least 1000 lux. The lighting industry and the paper industry know this, and this is why they've designed the paper and lighting to increase the amount of blue. So, as part of my PhD, I said that I was interested in seeing if the declines in literacy and numeracy, which are a big issue in Australia, in the last few years, you cannot turn on the television without politicians or somebody talking about further declines in reading and mathematics. I wanted to see if these declines were actually correlated or were a negative correlation of the increases in brightness and whiteness in the school environment. And it appears to be so. That long-term studies are difficult to find. There are a handful in the USA and a handful in Europe. In Australia, there've only been two, although this one by Thompson de Bortoli is more of a medium-term examination. Now, Lee and Ryan compared the results of Year 9 students in literacy and mathematics in these two time frames. The difference in the time frames is because they painstakingly found questions in the exams that were identical, so then you could actually have a true comparison. They found that kids in 1964 they measured up to 2003, and 1964 kids, by kids I mean children, were comparable to Year 10 children in 2003. In other words, they were almost one grade above with their standard of mathematics and literacy. And, as it says here, this is despite huge reductions in class sizes in the same period. Class sizes in 2003 are 43% smaller than in 1964, and the government is spending 258% more per child in real terms, allowing for inflation, in the same period. So despite extra money and smaller class sizes and more teachers, the children in 1964 were doing far better. So that supports my hypothesis. And the other study, which uses PISA, the International PISA test, which began in 2000, does not go back so far, but there was a steady decline. And since this study, later PISA results show that decline has continued, in Australia at least. And as you can see, 36% of students are below the baseline literacy level, and 42% of students are below the national baseline proficiency. Sorry, I need some water. The same has been the case for in writing literacy. In case anyone is interested, I'll just briefly skip through that. But here was Year 9, 30% of Australian students in 2010 were below the minimum standard in writing. So the implications, in my opinion, for education are that I found that the increased reporting of learning disorders in recent decades correlates well with the so-called improved brightness of school lighting and paper. Negatively correlates, I should say. Oh, no, sorry, no, it's actually correlates. Now, one other finding is that visual stress is not confined to populations with reading difficulties, and it does not usually prevent learning to read. I'm an example. Interesting finding from the study with the lighting at the University of Oviedo is that even PhD students and professors have visual stress. So those implications mean that perhaps the over-illumination in places like hospitals is affecting medical professionals with visual stress in high-stress situations. So that has implications. There are also financial implications. We're wasting a lot of money and emitting a lot more CO2, greenhouse gases, and so on, than we need to. I did two quick audits. I'm not quick, but I did two audits purely out of interest at my small university with only 5,000 students, 20,000 fluorescent tubes, which is 4 tubes per student. And I found that just by adjusting illumination to the statutory standards guidelines, that small university would save $250,000 a year, every year, and also reduce CO2 emissions by 1,000 tonnes every year. I also did the same thing at the University of Oviedo. It has 23,000 students and there are almost 4 lights per student. However, these lights, 80,000 lights, if placed end to end, would stretch for 100 kilometres. And at least 1/4, I would say half of these lights are not necessary. The minimum cost savings they would have there, simply by adjusting to European standards for lighting, would be almost €500,000 a year. And they would save 4,000 tonnes of CO2. So finally, I must say goodbye because I did have a timer, but it didn't start, so I have no idea how long I've been talking. I would like to thank the audience for their interest in my video presentation, and excuse my nervousness while talking. I'm not used to cameras. And again, I wish to thank the organisers of the Congress for inviting me to give this talk. So lastly, this spiral is not only, I put this here not only to represent the spiraling increase in brightness in schools, but also to demonstrate that everyone has visual distortions and visual illusions. For example, if anybody in the audience cannot see a spiral here, then they have superhuman vision, because there is no spiral. And most people cannot see that. It is because the human brain is tricked by the high contrast black stripes on a white background into thinking that these concentric circles, you'll see here, this is a circle. And the next one is, if you follow it, a circle. You come back to the same place. Each of these is a circle. This is how powerful visual distortions can be. The only difference for people with visual stress is their threshold for such distortions is lower. They have them, but it's more easily triggered. So for them, brighter lighting and contrast and whiter paper is a big problem. For the rest of society, it also makes life uncomfortable. On saying that, I better say goodbye because I've probably gone well over the time limit, but I thank you again, and I wish I could be there, perhaps next year. Bye for now. Thanks for your patience.